the recording. All right, great. So today we're very excited to have Frans Oliehoek talking to us today. So I'll give a little bit of his bio. He's an associate professor at Delft University of Technology, where he leads a group on interactive learning and decision making, and is one of the scientific directors of the Mercury Machine Learning Lab. He received his PhD in computer science from the University of Amsterdam and held positions at various universities, including MIT, Maastricht University, and the University of Liverpool. Frans' research interests revolve around intelligent systems that learn about their environment via interaction, building on techniques from machine learning, AI, and game theory. He has served as a PC, SPC, and AC at top-tier venues in AI and machine learning, and currently serves as an associate editor for the Journal of AI Research. He received the Best PC Member Award at AMOS 2012 and was awarded a number of research grants, including a prestigious ERC starting grant for his project Influence-Based Decision-Making in Uncertain Environments. All right, take it away, Frans.
All right, thank you very much. Thank you very much. Yeah, so like already briefly alluded to, I put in also in this talk some slides about a bit older stuff, just because I think, bringing kind of the background on some of the multi-agent work that inspired some of the work that I'll be talking about is quite nice and relevant for this audience. On the one hand, I hope I won't run out of time. On the other hand, if I really lose you, please stop me, type something in the chat. I'll try to monitor this, I suppose, and otherwise I'm sure somebody else can shout out. I think it's nicer to have you on board than to ramble on and make it on time, say. All right. Yeah. So let me dive in. So the title of the talk today is Influence-Based Abstraction for Faster, between brackets, multi-agent planning and learning. So there will be some multi-agent work, but the speed-ups that I will talk about will actually be mostly in the single agent or in the say best response setting. And then Miguel will actually talk about some recent work where we are speeding up for many agents. And in 2 weeks from now, I believe, right? Something like this. Okay.
Actually, next week, but yeah.
Next week already.
Yeah.
Okay, perfect. Let me jump in then. So the goal of much of my research and many people in AI, of course, is somehow designing intelligent systems that can potentially control complex environments. And so you can think of these problems like indeed controlling traffic in a large city, or perhaps controlling some UAVs that need to have some coordinated behavior, or perhaps control particular networks, perhaps to control diseases from spreading. And all these types of applications are characterized by the fact that there's potentially multiple actors. There's highly partial information at any particular location, simply because there's constraints on how much you might be able to communicate. And they have very large state spaces. So indeed, if we think of something like controlling traffic in a major city, so there's a map of Amsterdam, but think of Manhattan, easily there's tens, hundreds, thousands, or perhaps tens of thousands of state variables in such a problem. All right. So of course, this scalability directly ties into what is more or less the holy grail of sequential decision making, I suppose, the Bellman's famous curse of dimensionality. And of course, in recent years, we have seen tremendous progress by making use of deep learning. And the prototypical example, of course, is say DQN. Which brought a lot of scalability in terms of being able to directly learn based on images and to then spit out essentially how good the different actions are in these Atari games. Right. And so very roughly here, the idea is so just feed it into the deep neural network and let the neural network take care of the scalability problem. And of course, it's not that simple. I don't want to say anything negative about this work. I really think this is very important work. And it allows for huge improvements with respect particularly to sensor data. But at the same time, I also think that there is more we may need to do to deal with complex systems. Right, and so in this talk, I'm going to talk about more explicit forms of abstraction, if you will. Okay, so let me try and give a somewhat short and very incomplete as well, I'm afraid, of course, but a short history of some ideas of abstraction and value factorization in multi-agent systems. Right, okay, so I'm gonna go a little bit faster. I think most people in the audience here are familiar with these kind of formal models. So kind of like the basic model, say, that I'll be building on in the rest of the talk is the decentralized, partially observable MDP model, where essentially there's some set of n agents, and each agent individually selects its actions. And then as a result of the action taken by all of the agents, or the joint action, the state changes in some way. So there's some transition probability. Similarly, we assume that there's some set of joint observations, but importantly, each agent will only receive its individual observations, right? So they don't share their observations in this model. And of course, also there's some kind of joint reward function, which models how good a particular joint action is in a particular state. All right. Yeah, so I hope this is more or less clear. If not, let me know. I'm happy to elaborate, but otherwise I'll push on a little bit. So in these models, in these DEC-POMDP-like problems, often we care about these optimal planning tasks. Right now, there's a lot of attention, of course, on multi-agent reinforcement learning. 10, 20 years ago, we were somehow starting like, okay, well, let's first assume that somebody gave us this DEC-POMDP model. Can we then somehow try and compute optimal policies? And the idea was that, okay, well, perhaps we do this planning on a centralized big computer, and then, you know, we can just give this joint policy to the team, which will execute this policy then in the online phase. And of course, the question is, how do those policies look like? Well, in general, if you want to be able to get optimal value, right, the optimal policies, these policies are really mappings from histories to actions. So I imagine that we have somehow these two agents, the Pac-Man here, looking for some kind of target, say the ghost. Then a policy could be like, well, first go to the bedroom. Then if you went to the bedroom and didn't find the ghost, go to the living room. Otherwise, if you did find the ghost, stay, etc. Okay, well, of course, not easy or not difficult to see that if you are dealing with policies in this explicit form, the problem is going to end up being very intractable, right? Just the size of the policies itself is exponential. And so perhaps it shouldn't come as a surprise that solving these problems is provably intractable or NX complete. And in that sense, it's clear that they might be quite different from the single agent setting. And that's also the case if we think about what do we base the actions on. Like I said, here we need to have this history. On the single agent setting, of course, in say a POMDP, at least there's a way to summarize the history by means of a belief state. That's no longer the case here. All right, so what can we do with this complexity? So in this talk, I'll try and get across a picture of trying to combat this complexity with what I call influences. So try to, very high level, try and get across what I mean by that. So when we talk about interaction, really what we mean is that it is the combination of policies that matters, right? So we have somehow two agents, agent one and agent two. And for them to interact means that somehow what is the best policy for agent one influences what is the best policy for agent two, and vice versa, right? This is really what it means to interact. So then we can try and think of a abstraction layer in between these policies, right? So this is kind of what influence-based abstraction or influence-based policy abstraction, as we also called it in the past, tries to do. So somehow, perhaps not everything about the policy of agent 1 is relevant for agent 2, but there's only a abstract sort of influence that matters, and the other way around. And so the example that I like to use is, for instance, if a cook and a waiter need to collaborate on the work floor. Of course, there's some things that they need to know. For instance, the waiter might need to know if the steak was a medium rare or well done. But the waiter might not need to know all the details of how the cook then prepared that steak. Right, or a different example, which goes back to a paper by Raven Becker et al., and which is the first paper that I am aware of that investigates these kind of ideas, has this example of Mars rovers. So imagine that we have 2 Mars rovers, and they both have a mission taking them to some sites where some things can be done. But both of them have their independent mission and select their own actions, and they don't interact much, except for the fact that, you know, perhaps the one rover goes on one particular side of, say, a canyon, might be side A or something, and the other rover goes on the other side of the canyon. And then if they both would take the picture, perhaps you can now do a type of 3D reconstruction or something like that. So now the fact that both of them would have taken the picture brings super additive value, right? So they have the independent transitions, independent observations, but if they somehow take both the picture of the same site that both of their trips will pass by, then they get some extra value. And of course, it could be multiple events, etc. But I'll just go with the picture example. So in that case, from the perspective of the one rover, all that matters about the other rover is just whether the other rover would take the picture, yes or no. Or really, what is the probability that the other rover takes a picture? Right, and that kind of means that we can express the value in this sort of nearly factorized form, right? So you might be familiar with value factorization in multi-agent learning. But this is kind of similar. So here we now say, well, the value that the policy of rover 1 and rover 2 will generate, what's going to be the values of their individual missions, but there's also some joint value depending on the combination of their policies. Right, and so this is very close indeed to these ideas of value factorization. In value factorization, we typically assume that there is a somehow exact way of specifying the value function. Right, so this is an example from the so-called network distributed POMDP model, which was introduced by Nair et al. In 2005. So it also makes some of these assumptions similar to what the assumptions were here in the Mars rover example. So this was the transition independent DEC MDP model that was coined back then. This ND POMDP model had similar types of assumptions, namely transition independence as well as observation independence, but assuming partially observable environments more generally. And they showed that in those type of models, the value function of a joint policy would factorize in this way exactly. Right, so somehow there's here a summation over some components E, and then there's some, so that component also denotes which subsets of agents essentially participate in a value component. So you would have a value component for each of these components, depending on the policies of just those agents. Right, so put plainly, essentially it's kind of like this vector graph, if that says something to you, where all of these gray squares now correspond to the value components. And so, for instance, this is the value component between agent 3 and 5 that depends on their policies. Okay, well, why would we even care about this value factorization in this form? Well, if you have this, then actually you can now use this to more quickly do the optimization over joint policies, right? So this essentially now becomes a constraint optimization problem that you can solve with techniques like variable elimination or max plus. And of course, if you have a factorization where there wouldn't even be overlaps, so where I mean that all the values would only depend on an individual agent, yeah, then you can just do the individual optimization. And that is what we've been seeing much more commonly these days in the centralized training, decentralized execution, formalism for multi-agent reinforcement learning. Okay. So yeah, so this is great. That leads to speed ups in computation doing this. But of course, it still works in policy space, right? So what do I mean by that? Well, let me go back to this approximate value factorization that we had before, right? So this was for this transition independent DEC MDP, where we said, well, the joint value is the individual values plus somehow this joint value. You know, what we now discussed was this value factorization type of approach. There, essentially, we would say, well, perhaps this joint value can be approximated well by just, say, the individual values. And now this perspective of influences is slightly different. It would say, well, we can take this formulation that we have above here, but this joint value doesn't depend on the full policies. It only depends on these more abstract influences, right? So in this Mars rover example, the probability that each agent takes a picture from its side of the rock or of the canyon. Okay, so what does that really mean then? Well, so we can think of these influences as implying a clustering of the policy space, essentially, right? So there might be these policies of agent 1, and each of them leads to, all of these lead to, well, some particular probability of taking the picture from its side of the canyon. Well, so therefore, all of those policies will be mapped to the same best response of the other agent, right? They have the same influence, then it's going to be the same best response. And so that is what was exploited in what we now call influence-based search or joint influence-based search, right? So now here the idea is that if the space of influences is much more compact than the space of policies, so if the space of individual influences are much more compact than the space of individual policies, then certainly the space of joint influences is going to be much, much, much smaller than the space of joint policies. And so perhaps you can search through the space of joint influences and then independently essentially try to compute a best response. That's sort of the main idea behind these methods. Right, and okay, so this discovered set algorithm that was introduced by Becker in the paper that I mentioned was kind of like the first instantiation of this. So here you can imagine, of course, that now depending on the probability of the photo being taken by agent 2, each possible policy by agent 1 would have a particular value. And, you know, this is very much like a POMDP piecewise linear convex value function, if you've ever seen those. And so you can try and just find all possibly optimal policies for agent 1 in this manner. Right, so building on these ideas, we also did some work. I did some work with Stefan Witwicki and Leslie Cabling now a decade ago, where we came up with a form of optimal influence search and an A* form of that for slightly more general problems, and there have been a whole set of other problems as well. So I'm highlighting this, well, both because, well, it connects to what I'll talk next about, but I also think it's nice to perhaps consider some of these ideas again. And so these were some prototypical results that we had again. So this is planning, but so restricting to searching in these influence spaces can really bring you a lot of speed up. So here, this is the solution of some benchmark, but the point I'm trying to get across here is the massive improvements in terms of runtime, because this is log scale here. Yeah, so you can see you can really do orders and orders of magnitude better. Okay, so that is somehow my history of some of these ideas. Now let me try and move a little bit more to how we are using influence-based abstraction more recently. All right, so and so the important bit here to also realize is that all those examples that I just showed you, they were exploiting, specific structure of specific special cases of decentralized POM-DBs. Where there was either transition or observation independence or both, or reward independence. So what if we want to somehow do this now for general tech POM-DBs, these kind of IDs? Well, first we will need to somehow exploit some type of structure. And so what we'll do is we'll represent the transitions, observations, etc., in some structured form. Specifically, I love to make use of this language of dynamic Bayesian networks. I think many people will be aware and familiar with these. But just very quickly, so the rough idea is that if we have this kind of like complex problem here, we might be able to somehow encode that in terms of state variables. So for instance here, how busy is road segment 1, as well as local action. So what is the action of intersection 2? And then we can think of, okay, what's now the probability of road segment 1 being busy at having high density or low density at the next time step. And that will then perhaps only depend on a subset of these variables, right? Because there's some locality in the system. Well, okay, in this way, of course, we can, create this entire diagram specifying the probabilities at time step t+1 given what we did at time step t. We can also add in perhaps these observations. So we'll assume that there's going to be these localized observations. So the observation of intersection 2 depends on the local state variables. And perhaps we also have these kind of like localized rewards. So again, so you can think of this factored reward function. So now it's the rewards that are factored. It's important, the rewards are factored, the values are not here, right? So in a traffic system like this, over time, things will propagate, right? So we can think of it in this way. When we unroll this whole network over time, somehow to predict the reward 2 time steps into the future at intersection 2. At time step 0 here, you would need to include all these state variables. Right, so there's not this factorization that we had before. Instead, we have that all these factors, are completely coupled. Of course, we might think that this coupling is somehow gradual. So perhaps the influence of, say, x4 here on this reward 2 time steps into the future isn't so big. And then, we might get away with this kind of like approximate factorization. Right, so that's now one of the things that we also tried back in the days. Somehow you take this problem based on the DBN, we decompose it in a number of subproblems. Right, for each of those subproblems, we now define these sort of source problems. So we now have 3 independent 2-agent problems, say. So then we solve those, and we put them in a type of plan repair phase to pick the best coordinated joint policy, essentially using the same type of max plus or variable elimination types of approaches that we saw before. And doing that can actually work quite well, right? So on some of these DECOM-DP benchmarks, we got some quite good performance. Also, at HKI 2015, we had this paper where we actually compared to upper bounds on the value function that we were able to compute, also making use of the factorization, and then saw that, you know, for some of these problems with 50 or even up to 100 agents, the quality was really very good, so essentially optimal. And also in a more realistic type of setting, we try to do this for coordinating deep reinforcement learning agents that control Sumo. So indeed, we did this kind of decomposition, and then for the different subproblems, we essentially put on reinforcement learning agents in Sumo that computed the value function, and then in the online phase, those value functions were used to coordinate in online fashion, right? So that was, I think, actually one of the first, value factorization approaches to deep multi-agent reinforcement learning. Okay, so empirically, all of that was quite nice, but the question, of course, is it's really not so clear how you should define then those abstractions, or what could go wrong. In the end, it is just a more or less arbitrary kind of source problem that we defined and solved, and that might not be the way that that part of the network would operate when it's connected to the real network. And that is what we've been really trying to zoom in on in this influence project, right? Can we somehow better understand these abstractions rather than somehow defining a local problem and solving it and hoping for the best? Can we somehow understand really how this local problem now influences the global problem and the other way around? And just to give kind of like a cartoonish example of this, there's this sort of cartoonish example. So imagine that we're trying to control here this intersection A, and at time step 0 now some of these cars arrive, and so that means that perhaps intersection A might be inclined to give the green light, which means that then there's going to be more cars in the next time step at intersection B, which might mean that it gives it the green light again, and perhaps relatively little traffic going to C, which then might mean that, again, one time step later, there's a higher probability that intersection C will give the green light to the southwest-bound traffic, which, of course, then could mean that there's going to be an increased chance that the cars will arrive here 5 time steps later. Right, so somehow what we've seen here is that based on the history of the local intersection here, we can better predict the arrivals of some cars from this particular direction, say. Right, so zooming out a little bit, if we somehow can remember the relevant things of a local problem, we may actually be able to very well predict how we will be influenced in the future, and use this to have some kind of principled forms of abstraction. All right, so where are we now? Ideally, we want to control complex systems, and so the idea is to try and decompose them into local problems. How to really do that, because these local and global problems influence each other? Well, we'll try and explicitly represent the influence between one and another by remembering relevant parts from the local history and use those to form these principled representations. So a question here, is the decomposition learned or predefined for each problem? So in our work, we have mostly manually constructed the decompositions. The type of problems and benchmarks that we've been looking at, that was quite reasonable to do. I do think that there is still an open research question of, how could you perhaps optimally select that? There's different trade-offs, etc. But yeah, mostly manual so far.
Thank you.
All right. So let me try and get across a little bit of then how these representations really look like, because of course everything has been quite cartoonish so far. And so in order to do that, so we're going to focus in now on this form of doing the abstraction. So somehow agent 1 here is, say, the rest of the system, and agent 2 is us, and we're interested in the influence of agent 1 on agent 2. So this means we're also going to adopt this best response perspective, right? We're going to somehow care about the problem for agent 2, the local perspective of agent 2. And so that means that actually I'm not gonna fully deliver on everything that I was hoping to do, namely the entire control of the complex system, right? I'm focusing on a simpler problem, namely the best response problem of, say, one intersection. That's important to keep in mind. And then, of course, the hope is that that might help in solving the bigger problem. And next week, you will see some evidence of that.
Can I ask you a question?
Absolutely.
Yeah. So one thing that comes up throughout this talk is it feels very close to this area of like mean field games, where and I'm wondering if there's a close connection between these two, or whether they might just be different names for the same thing.
It's a very good question. Yes, I believe so. I was also trying to explore this a little bit in collaboration, which, well, it got a bit delayed. It's on the agenda. To some extent, the mean field theory, of course, explores the limit of somehow infinite other agents that influence you in some way. And here, really, we try to make very explicit what if it's not an infinite number of other agents, but a finite number, and how are you influenced in that way?
Thanks for the clarification.
Yeah.
Yeah.
No, question. Great question. How am I? Yeah. I'll need to hurry up a little bit, but okay. So let me try and get across now what these influences are in a problem like this, right? So suppose here we're zooming on now the local problem of agent 3, right? For which we want to say compute the best response to however the other agents, the other intersections are programmed. So then we can think of, well, somehow zooming in on this sub-problem, where this is now the problem that agent 3 cares about, its actions and the state variable surrounding its intersection. And somehow there's this other part of the system that we want to somehow abstract away. So if we do that, so it becomes apparently directly clear that in order to somehow reason locally, we will need to do something about these links that are pointing into our local problem, right? So somehow we think of the sources of these links as the influence sources. Then if we would know their values in advance, so I think it's okay, so some assumption, I'll come back to that. But if we know their value in advance, then essentially we could do localized reasoning, right? We could do local planning or learning or whatnot. But there would be no dependence on the rest of the problem. Of course, we can't know these values in advance, but we can try to predict them, and that's going to be the upshot. So here, this also clarifies a little bit the assumptions that we are making. The sub-problem here needs to contain all the observation relevant variables. So these are commonly P's, and what we're abstracting away, those are all latent variables. Anything that influences our observations needs to be in the local model. And the same holds for the reward variables. So I didn't show the rewards on this picture, but also here so now the reward of agent 3 just depends on its local variables, right? It only cares about, say, the traffic throughput at its intersection. Of course, those are somehow limiting assumptions, but this is what we can do some real exact reasoning for. All right, yeah. So this was the reasoning that I already told you. So if we knew the values of these influence sources in advance, then we could do local reasoning. So we don't know these values in advance, but instead we can try and compute a distribution over them. And that is essentially what we call an influence point. So an influence point is now a collection of conditional distributions. So it's a collection because we have one for every time step. We are trying to do this exactly. So somehow we think of these finite horizon problems, and then for every time step in that finite horizon problem, you have a different prediction problem. But so, for instance, to predict this, to be able to predict the value of x3 here, you would need to predict the sources here, so a5 and x4 at this time step t equals 1, say. All right. So that's nice to some extent because, this is something that we know about, right? It's an inference task. And in order to predict these sources, we will need to somehow remember some things. We'll need to condition on some things. Turns out that if we somehow find a deseparating set, so we deseparate those influence sources from, essentially all the other variables in our local model that we do not condition on, then we are good. All right. So, that's nice because that means that we can actually transform this complex model into something that looks like this. And we can have some theory that actually says that this is without loss in value, right? So what this says here is that for all the policies that the other agents might use, the value that I would compute in this POM-DP, the best response value that I would compute in that big POM-DP is going to be the same as the value that I would compute against the influence computed for their policies, right? So this is somehow exact. So that's nice, but of course there's a catch here, right? So this D, the thing that you might need to condition on, in general, that could be huge. And generally, that could be the entire local history of the problem. On the plus side, we do know many classes where, you can actually represent it more compactly, but in general, perhaps not. Okay, so that's where approximate influences come in, and where I will spend the remaining time after what I want to compute to discuss next on. Let me skip somehow these things. So yeah, this is a more concrete example. This comes directly out of the Jair paper that we published last year. So if you want to know a bit more details how this really works, that will be the best source to look at. Let me jump here, because for this audience, I do want to cover somehow what is the implication, now what I've been saying, perhaps for multi-agent reinforcement learning, and things like value decomposition there. Right, for instance, if we think of value decomposition networks, they do these individual Q decomposition, right? Somehow the value of a particular joint history and joint action is approximated by the sum of individual value functions, individual history, and an individual action. Right, and the main assumption we make and exploit is that the joint action value for the system can be additively decomposed into value functions across agents. And that sounds like a pretty big assumption. But somehow, when we think of it, this theory of influence-based abstraction does show that there's actually quite a large class of problems for which this almost holds. Almost. And let me explain that. Right, so what we show with this theory is that in these so-called local form models, so these models that I talked about, where the observation relevant and reward relevant variables are in the local model, and the rest is latent, and we do this influence-based abstraction, for those models, we have that for any policy, the value of a particular history is the sum of these. These are now local values computed with influence-based abstraction. So BL is a local form belief that includes the effect of the policy of the others. Right? And so that also means that, you know, if pi happens to be a Nash equilibrium, we also actually have this type of decomposition. Somehow, if every agent in pi is playing a best response against another, then, you know, that also means that this value is actually somehow taking the maximum action value. However, it is not the case that Q under pi and the joint history and the joint action is exactly a sum over individual terms. So why not? What's the difference here? Well, so in these values, so that the values computed in these local form models, we assume that other agents act according pi, right? So this Qi gives the best response value, if you will, as long as the other agents play pi. But pi might not specify action A. Right, so you have this kind of like you're almost correctly predicting the values, except for the fact that, you know, you're now asking about a query value for a different joint action that was not specified and was not represented in your values here. Okay. So yeah, what is the take home from this? Well, perhaps, you know, in many of these problems, this factorization is relatively good, but it could somehow be that value factorization, therefore, you know, has this kind of like on policy characteristic, if you will, right? Because these local values, they will somehow try and fit to values according to the current policy being taken by the other agents. Okay. So yeah, I think, you know, it's left open to explore if that has any implications on really how to design better, perhaps these value factorization methods. Okay, I think so. So can I try in the last 5 minutes still to flash by some of the things that we've been doing, and then I have perhaps 5 minutes left for questions. Okay, so this is going to be very fast, and then well, Miguel, who is also co-author on much of this work, might actually still give a short recap or something if useful. So the idea here now is to use these kind of ideas to speed up online planning, right? So okay, so let me just flip through this a little bit. So we've been talking about these exact influence points that would be great to have. In general, we might not have them, so we're going to replace them somehow by, you know, say influence predictors or approximate influence points. And essentially, these are now just machine learning models, say a recurrent neural network, that make these kind of predictions. Of course, then you can ask, well, how, you know, what needs to hold for a good, what makes a good approximate influence point? We had a little bit of a theory here. It seems hard to have any firm guarantees. You very quickly end up, you know, having to make firm guarantees about a deep neural network, and therefore, you know, asking about hard generalization guarantees. But at least it seems that doing some of these things is well aligned with using normal machine learning techniques. Okay, so then the rough idea is essentially as follows. Let me just jump right into this kind of like algorithm where we would do this online planning, right? So this is now being transformed in the following way. In step 1, we first learn a approximate influence point by first using the global simulator, a simulator of our big, large problem, to learn these influence predictors. And then in the next step, we use now a local model which uses this approximate influence predictor to predict the missing variables to do much faster local simulations. So essentially what we do is we trade off time spent offline to now be able to plan quicker in the online phase. Right, so we investigated this into also benchmark problems. So here the first thing was kind of simpler, kind of grab a chair domain. So the agent goes to the left chair or the right chair, and so do the other agents, and somehow it needs to learn about how it's affected. And also here on the right, we have this more traffic-inspired kind of problem. So this is a little bit like a traffic problem with cars flowing through. Let me flash you the type of result that we got. So here is this grab of chair domain. Right, so here what we saw is, so green is using the global simulator. That's simulating the entire problem. So if you scale the number of agents, that time goes up rapidly, of course. Blue is when we use random influence predictors that are not trained. So that's very fast, of course, but the quality is poor. And then if you do the actual training of the influence predictors, you get a good scaling behavior and also good performance. The other domain we also looked at, and here we looked more at the anytime behavior, right? So of course here also, here this is how many simulations per second we were able to do for the different models. So green again is the global simulator. So we're able to do fewer simulations, and that means that if so this bottom plot is the performance for X seconds of plan time. That means that if we have 60 seconds of plan time, we're doing very well. But if our budget is tighter, we see that our approach just does a lot better. And of course, here again, blue is again these random predictions. We can do a lot of simulations, but they're not high quality, so the performance plateaus off. Okay, so this was trading off time offline to be quicker online. What if we don't want to wait, you might wonder. Well, so this is also something that we explored. So we had a paper last ICHCAI where we had this kind of mechanism which lead to what I call essentially like a self-improving simulator. So the idea is that some history comes in, then we ask if our predictions using the influence approximate influence point or influence augmented local simulator are accurate. If not, we'll use the global simulator, which is going to generate data that we can use to train now our local model. If we think it's accurate, then we'll just use the local model. And so it proceeds. And of course, doing this is far from trivial. Here's where a lot of the nitty-gritty is happening. Somehow are we trying to estimate KL distances, etc. online. So it's actually not so easy or straightforward to get to work. But somehow it is possible. And we got quite nice results here, I think, where, so okay, let me see. So here this gray line is somehow the baseline of just using the global simulator. And of course, so we see that we have some startup costs. These different lines are for different values of a hyperparameter on how much to penalize this global simulator. But if you pick that hyperparameter right, then you can start to do much quicker simulators relatively quickly, and that will also lead to then quickly getting better returns. All right, so yeah, that was the results that I wanted to cover today. So those are indeed in this best response setting, so essentially single agent. And Miguel has now some really awesome results on doing this in Sumo using the flow framework, actually, for up to 100 intersections, I believe, right? All right, so that's next week. Yeah, let me just summarize I've given this perspective of trying to interpret complex systems from a local perspective. How is this local problem influenced by the rest, and how do we potentially influence the rest? And a bit more detail, I try to get across, where the motivation of this work came from in the multi-agent planning community. We talked about the general case of defining these influences in factored DECPOM DPs. I tried to cover a little bit the relation to value factorization and these influences, and quickly showed some results on using these approximate influence representations in online planning. Yeah, thank you for bearing with me. Indeed, I think I overdid it a little bit with the amount of stuff that I wanted to cover here. But I hope it was interesting nevertheless, and I'm more than happy to answer any questions still now, or if you want to email later also.
Clapping over Zoom is hard, but we try.
I know it's
sorry. Thanks so much for the talk. I think we probably have time for maybe one question, maybe two, depending on how long the first question is. So I'm just going to open the queue. If somebody wants to ask a question, I'll mute myself.